All right, so we'll go ahead and get started. So today we'll talk about systems operations and dispatch in practice. So, in previous lectures we talked about the market so that you guys understand essentially, how the system is meant to operate. And if the markets could operate, perfectly, and if we could understand forecasts perfectly, right, we might not necessarily need such a large and robust sort of operations aspect of your system operator, right? But the important thing to remember is that those markets produce schedules, right? They're not actually producing electricity. And reliability, which is one of the keystones of our system, is not totally automatic. There is a lot of active maintenance that needs to happen. And so we're going to talk about all of that today and what the operators are sort of having to manage. So uncertainty constraints, time-coupled decisions, right? And so I guess the fundamental question for today is thinking about, if our market is clearing, why do operators exist and have all this work to do? Okay. So remember, the operation of the grid is kind of balanced between a couple of different stakeholders. We're focusing a lot on the, ISO and RTO operators, but utilities have to do things. There's reliability coordinators that also have to do things. And today we're not really going to focus on any particular stakeholder. We're going to see how all of these guys work together to make sure the system is operational and reliable. Okay, and so remember, our main objective for the operators is balancing supply and demand continuously, right? And so anytime I request electricity, some power plant needs to essentially provide that electricity. The way we monitor essentially the health of that balance is through frequency. That's like the most clear signal for whether or not loads are being met by generation. And in balancing these two, having too much generation or too little generation, right, relative to the load can be dangerous. And we'll talk about a little bit more specifically about this in just a moment. And remember, all of the stuff that the market does to schedule out things, right? Imagine that if the market, or if those forecasts are not getting things perfectly right, which would be very difficult, right? Then you're always going to have a difference between kind of what's scheduled and what you physically need on that system. And so we're going to look at what it takes to kind of make sure that those two things, that you can deal with this perpetual difference between what's scheduled and what you actually need. So this is like a pretty typical day for like a grid system. So this was someone literally had like an oscilloscope on part of the grid where they were essentially measuring frequency of WEC, right? So WEC, remember, is all in sync throughout its entire grid. And you can see, right, frequency is not flat. We cannot maintain perfect frequency on the grid, so that is to say, perfect balance between supply and demand. But also note the kind of units here, right? So you're off by sort of hundreds of hertz on the y-axis. And so this is kind of the sort of deviations. And we'll talk about what happens when you get larger and larger deviations from are 60 hertz in the US. Okay? Any questions about this so far? All right. So frequency control, how do we maintain frequency? So right, as I was just mentioning, nominal frequency in the US is 60 hertz. That's true in the WEC, the Eastern Interconnect, and ERCOT, but they're just not in sync, right? Okay, when your system is balanced, you have mechanical power in the generators that are sort of equaling the electric power consumed by load, minus any losses that you have in the system. The rotational speed of any motor on the system is actually going to be constant and in sync with the grid. And balance means that your frequency is holding at or very near 60 hertz. So that graph that I just showed, typical day, that would be a good indicator that our system is fairly balanced. Okay, when we have too much generation, when your generation exceeds your load, frequency rises above 60 hertz. And what happens is you have these things called governors that will actually have turbines start to try and reduce input power as a way to reduce the amount of generation. And then there's something called an AGC, which we'll talk about a little bit more in a moment. This thing is sending signals essentially to reduce generation. So if unchecked, you may have certain protection devices starting to activate. Some generators might even trip to protect mechanical components, because remember, this stuff is spinning kind of in sync with the grid. If you're getting too high, the stuff is going to spin, it can spin too fast. Okay, and then you have underproduction. This is when generation is under your required load. And what ends up happening is your load starts to try pulling energy from your generator rotors, and so the rotational speed is going to slow down. And so your frequency will start to fall below 60 hertz. These governors that I was just mentioning will also help to try and increase mechanical input to start to get generation back up. And in response to underproduction, you may have things like reserves starting to deploy automatically, and in more severe cases, right, operators will try and step in and start to redispatch generators, right, in an effort to prevent this from becoming a larger problem. We generally consider underproduction to be maybe a little bit more problematic than overproduction. You can get cascading failures maybe a little bit more easily in this case. Yes?
How does the electrical load pulling energy from the motors cause the speed of the rotation to slow?
Yeah, so the way I would think of it, can I use the water analogy here? There is like momentum in the way that the grid operates, both in momentum is a weird way to describe this, but in the sort of electricity itself, and in the physical rotation of your generators and turbines. So you can think of essentially extra load or load that's not being satisfied is trying to like pull harder on the electricity, which is causing this stuff to go out of sync physically. So that kind of like friction in the system is going to slow things down. Okay. So cascading failure that I was just mentioning. So what can happen? So this is not to scale. This is the same plot as before, just using a plot to sort of demonstrate kind of scale here. So if you fall below 59.8 hertz, these governors that are sort of these automatic processes that help tell generators essentially to back down or start producing more. So once you fall below 59.8 hertz, right, which means you are underproducing, the governors sort of fully engage and tell the generator to try and produce more. Your primary reserves start to respond, and then operators have a small amount of time to try and bring in that generation to stabilize the grid. Right, and so if this was the typical day, and I'm saying 59.8, right, this is 59.98, 96, right, 59.8 is like way down here, okay, so the magnitude of this is quite different from what you would experience on a sort of day-to-day basis. 59.5 hertz, this is when a lot of those protection systems will begin to go off. And so this is really meant to protect your generators and turbines physically from like tearing themselves apart. So generators will trip. And then this is where you're bad enough that like utilities may try and actually load shed. And so to prevent, right, so you get this cascading failure where the frequency will continue to drop as generators start tripping, you produce even less power. And so one way to combat this is you turn off power to your customers, basically. So that's what load shedding is, yeah.
Is this plot an actual plot of cascade failure?
No. This is, I could not find a plot of, I mean, I'm sure there probably is, but this is more to give some sense of scale relative to what would be happening in cascading failure, right? So that's 60 hertz, 59.98, 59.96. If you're going below 59.5, you're like way off the chart, right? Yeah, and then below 59.3, severe risk zone. This is where you're causing physical stress to a lot of that infrastructure. And it's pretty likely that you lose the ability to kind of keep things in sync, right? This is like widespread blackout territory.
So when you say load shedding, is that like brownouts?
I can't remember, what's the difference between a brownout and a blackout?
That's a good question. As I understood, like brownout was like certain parts of the system went down, not like the whole system, or maybe it's flickering, yeah, I'm not exactly sure.
So, load shedding just generically refers to any time where I am shutting people's power off, like customer power off, in order to deal with some of these like issues on the grid. So maybe brownouts might have something to do with it, but it's not. So brownouts, blackouts are kind of a product, I guess, of load shedding. But really the main idea is if you get rid of the demand, well, okay, you're not getting rid of demand, you're getting rid of the load. If you get rid of the load, you can balance supply and demand on the other side of things, right? Because your supply side, you're in trouble, and usually we don't like touching demand, but in these kind of cases, you might have to. Yeah.
I just want to say, in a brownout, power doesn't go off. It's just that voltage goes a bit low. Power is
Okay.
still on,
A brownout is just lower voltage.
so lower voltage.
How does that? Okay, I have to think about how that works. Okay. Yeah. Below 59 hertz, this is very bad news. You're going to have generators tripping all over the place, which means that you're almost certainly going to have cascading outages because, yeah, your generators can't keep up, so they just decide to essentially get out of there, which makes the imbalance between your supply and demand even greater.
So when does a cascade generally begin? Like if they can't stabilize it solely using the governors and then generators start to trip,
Yeah.
that's a potential cascade. 'Cause,
Yes.
like, you have no chance, at least within seconds or minutes, of like serving the load that's now going even more underserved.
Yep. Yep. Exactly. Yeah, so this does, I think, what most of you guys would expect, right? Uncontrolled frequency collapse leads to the generators tripping, motors stall, try to draw excessive current. Protection relays will trip in your transmission and distribution systems, and then entire regions may sort of black out. So this stuff is bad and something that you would hope to avoid, right, as an operator. And so what things do we have to help control frequency? So we can think of this in a couple of different layers. You have primary, secondary, and tertiary forms of protection. The primary, so think of primary going down to tertiary. Primary things are happening fast and most often are very sort of automatic types of protection. Going down to tertiary where things take longer, and this is where actually operators are stepping in to try and intervene. So governors, inverters, these are devices that are sort of coupled with your generation assets, for example, that will try and protect against frequency deviation. These things are sort of automatically looking at the frequency on the grid and giving these signals to your generator to kind of ramp up a little bit or ramp down a little bit. Okay. The AGC, this is things that are the automatic generation control. Hold a thought on that. We're going to talk about that more in just a second. And then tertiary, your operators are essentially trying to dispatch reserves and even redispatch certain systems in order to deal with frequency control.
Can I just ask a question?
Yes.
What is that MTDC?
MTDC, where's that?
MTDC, primary frequency control, secondary frequency.
Oh, in the plot. I don't remember.
I guess it could be a balancing element or something.
It's multi-terminal data count.
What was that?
Multi-terminal data count.
Okay, so multi-terminal direct currents.
So what it means that in an normal HVDC system, you would have two converter stations, but in a multi-terminal DAC card, you would have three converter stations, something like that.
Okay. I'm trying to recall what I was thinking with this figure when I put it in. What does that have? What did the converter stations have to do with the frequency control? I don't remember. I will look into that and get back to you on that. Okay, so primary frequency response. Yeah, so the governors are the things that detect how the frequency is changing, and then they will try and proportionally increase or decrease the, on the mechanical side, the generator and the turbine, essentially trying to proportionally increase or decrease the generation to make sure that you're staying balanced on the frequency side. So this is all automatic, no operators need to do anything. This is constantly happening, right? These are kind of the very minuscule deviations that you have in real time. And so the response happens very, very quickly, but the magnitude of the response is maybe a little bit more limited relative to the other types of controls. You also have inverter-based resources, and they can provide certain nuanced types of responses, even faster than governors, but in magnitude even less in terms of the sort of energy provided.
What's a group-like response?
So it is a particular shape in the frequency that you might see that these things are sort of well positioned to respond to. And so this is like a sudden like droop in your frequency.
Voltage drops are bad.
Yeah.
Sudden drops.
So we think of primary response as something that will buy you time, but not necessary stability if things are starting to go out of whack. Secondary control, so you have the automatic generation control. So this is kind of a system-wide signal that continuously adjusts generator outputs. So this is something that can correct like interchange deviations between balancing areas. So an AGC has kind of a broader view of what's happening on the grid than governors, which are sort of attached to your individual generators. So you have a control center that essentially measures system frequency, and if there are errors between different interchanges that are happening. So they have this area control error that gets measured, and then this sends out a signal to all of the units that are sort of regulated by this AGC to respond in a specific way.
So does it like put on a brake or something?
Well, it could put on a brake, but it also could hit the gas, so to speak.
Yeah.
Yeah. So it can go either way. A lot of times, AGC is going to be connected to what we would call sort of more fast responding units, right? So these are things that can provide quick ramping services up or down to help stabilize frequency.
Hold on just a second.
Yeah.
I need time to like digest that.
Yes.
So the ECI and the governor is a control system.
Is a what?
are both of AGC and governor, is that a control system?
Yes.
What's the difference then?
So the governor is looking at things very locally. So it is sort of attached to an individual generator, whereas an AGC is looking at an area control. So they look at errors and deviations at like a larger scale.
So AGC is much more on the system than on the turbine or the.
Yes, yeah, exactly.
How big are they in terms of systems?
As in, how many like power plants does an AGC like operate?
Sure.
I actually don't know. I mean, these interchanges, I mean, you can have many different sizes of interchanges. So AGCs are probably controlling systems of like varying scales. But you know, you're talking about sort of multiple generators as opposed to like a single turbine generator type thing with a governor. Yeah. So the AGC will help with like persistent frequency deviation. So if you're like off by a little bit, scheduling errors in your tie lines, small continuous imbalances. And so if you think about the way in which we operate the market, and then you have to make a forecast, and then you true things up on the real time, right? All of that scheduling that happens, you know, you may still be not perfectly matching. You may be sort of persistently slightly off, and the AGC is able to handle these types of things. Once you're getting to a point where you have sort of more severely mismatched the generation and load, that's when you start getting into the sort of tertiary control where you need operators to kind of redispatch things, right? And so larger contingencies, transmission overloads, fuel supply failures, prolonged shortages, these are things that are going to cause much larger deviations than the AGC can handle. Yeah.
This may be a basic question, but who runs the agency? Like, does each company have like really sharing the system, or is the whole system all companies are unified to use?
You're asking like who owns the
Yeah.
AGC?
Or like what's the role of companies within the system?
Yeah, so it's like it's an automatically running system. So it's not like a company needs to really actively manage it. But I don't actually know who would be the like entity that would be responsible for like owning and maintaining the AGC.
Is this like one of those, like, what are like services that's?
Yeah, because the thing is an AGC. I think I would think of it as mainly associated with the generation assets. In which case, like in a restructured market, I don't think it would be the utility because they don't own the generation. And CAISO doesn't typically
It
own.
has to be the ISO.
It
It has to be ISO, isn't it? Because you cannot give the system to an independent operator.
Yeah.
It won't make sense because they could manipulate it.
Yeah, I guess that makes sense.
It has to be the system operator, the end system operator, which is the ISO.
Is anyone able to look that up really quick?
I guess could be prescribed by the ISO, but actually owned by whatever utility is directly responsible for balancing that power.
Yeah.
Or maybe not, I mean, not owned, but installed.
It's run by CAISO. Okay. Okay.
You could probably have something that's owned by someone else, but CAISO's able to dispatch it.
Right.
Maybe.
Yeah. I don't know who would want to actually bother like owning an agency. I don't know how you would like make money necessarily, but yeah.
Could be kind of just like a per time expense, like, hey, we will remain available
Yeah.
for this daily fee.
Yeah, interesting. I've never thought about that. But okay, run by Kaiso. There you have it. Okay, and then our tertiary control, sort of manual redispatch, right? So operator directs changes directly to generation, right? So they say, these generators and these reserves essentially have to turn on or turn off. And so this is what's happening, in the timeframes after your primary and secondary responses are stabilizing the system. And so if you perpetually have frequency deviations even after your primary and secondary controls are stepping in, this is when you need manual control. And the primary and secondary are essentially buying time for you to be able to do this type of thing. So committing additional generators or decommitting units if you're overproducing. You might be dispatching reserves in a specific way geographically. You might be calling on demand response, and then you could actually be adjusting some of your scheduling. Okay, any questions? Okay, and so what operators are actually watching? So they're looking at things like system frequency, right? This is one of our strongest signals for the health of the electricity grid. The area control error, which is what the AGCs are looking at. Reserve deployment levels, and so as you think about any of these contingencies happening and you might be using reserves, you're actually required to have some amount of reserves in order to deal with this stuff. And if you're starting to eat into some of your reserve units coming online, you need to kind of prepare for that as like a contingency, and seeing what you can do to alleviate the use of those reserves. You're looking at generator availability and ramp rates. So say everything is actually going totally fine, everything's kind of peachy, your frequency is kind of within the bands that are totally acceptable, but you're using up all of your generators, all the stuff that ramps quickly is kind of being used up. There you have some alarm bells going off, because if something were to happen, your ability to maybe respond to that, if it's a sort of larger scale issue, is diminished, right? And so this kind of helps speak to your capability. Well, the reserve and your generator availability and ramp rates speak to that availability. Same with transmission loading, right? Everything could be fine, but your transmission is heavily congested. You might worry that if something were to happen, you can't transmit power to where it's needed. And so operators are keeping an eye out for these things, right, as sort of like making sure that your backup is ready to actually provide that service. Yeah, weather and load forecasts as well. Obviously, if there are big changes in the weather or changes in what the load is doing, you need to sort of adequately prepare for that. There's a really nice example of Kaiso actually doing a really good job of this with the solar eclipses, right? There's been 2 in the last like 10-ish years or so that kind of severely affect solar output in California. And so in both of those cases, they were like, I mean, this is a very foreseeable event, obviously, but they were able to kind of prepare their resources for a sudden decline in solar production. Yeah.
Would reserves be various storage assets or just like spinning reserves?
Both those. Yeah, we'll talk about some ancillary services, which include some of the reserves. Yeah. So yeah, for the area control error, this is in the actual interchange minus your scheduled interchange minus 10B, which is a constant for frequency bias. That's a value that the operators will choose, and they look at the difference in frequency. And so this is, yeah, if you're interested, the way that you calculate the area control error.
What is the interchange?
The interchange are essentially like small areas of the grid. Yeah. Yeah, and so when do they actually intervene? You let your controls, automatic controls work, you make adjustments, and then if needed, you call emergency procedures. And then as an absolute last resort, if none of this stuff is working and you're in dangerous territory, you shed load. So operators intervene when primary response doesn't fix your frequency, when AGC saturation occurs, when reserves fall below thresholds, and then when contingency probability increases. And that all of the contingency stuff I was talking about are those sort of latter half, this stuff. If all this stuff starts looking not so great, yeah, that's when operators may step in to take action. Okay. So, ancillary services. So what are these? Whereas we think about the sort of wholesale market and the assets that provide electricity as a way to supply the energy, ancillary services are tools that are meant to keep the grid stable, as opposed to necessarily thinking just about that like bulk supply meeting demand. So markets schedule energy. These services provide certain capabilities, right? To respond quickly, to absorb uncertainty, and to survive contingencies. So we think of a broad set of categories of ancillary services: regulation, spinning reserves, non-spinning reserves, supplemental replacement reserves, and then voltage and reactive power. So regulation, this is the sort of continuous fine tuning. So these are things like the governors. Then we'll talk about some of the spinning reserves that happen in slightly longer time scales, non-spinning reserves in even longer time scales, and then supplemental and replacement reserves, even sort of longer than that. Yeah.
So contingency in this context is just like an unforeseeable event.
So you're talking about a couple slides back. So the ancillary services, this contingency is, yeah, thinking about when essentially the infrastructure that you have to deal with some of these things, like frequency deviations, are starting to run out, I guess. So things like the amount of flexible generation. What else was there? Reserve deployment levels and how much is loaded on the transmission lines. If those are all running out, that would be like a type of, that's when you step in to deal with like that type of contingency.
Okay.
Yeah.
Did contingency have a different meaning to sensible?
I mean, I don't know. It's like a generic definition of contingency. It's like a backup plan essentially.
Okay.
Okay, so regulation services correct these continuous mismatches. So, you know, these would be your why am I blanking on it? The governors and the AGCs. This is all like fast response. So this is the stuff that we've talked about, right? And spinning reserves. So these are resources that are synchronized with the grid. They're basically able to increase output immediately, right? As opposed to something that needs to turn on, spin up, and sync up with the grid frequency. So these things typically will respond very quickly. And this can help, arrest frequency decline after like a big event happens.
Question.
Yes.
So if spinning reserves are already, they're just not generating power, but they're being spun already, I guess?
Yeah. Yes, and actually, from a services perspective, you get paid to essentially just sit there and be a backup, right? And so, even though you're not contributing electricity in the sort of normal market, you actually get paid to you essentially get paid to be a spinning reserve, whether or not you end up providing electricity, and so there's like an entirely separate market for a lot of these ancillary services that are essentially providing incentive for those services that are meant to provide reliability as opposed to provide supply. Yeah.
Would these be like distributed throughout the grid network, like, on a smaller like capacity compared to like a power plant?
Like you're saying, like where they're located.
Yeah, would they be like, would it be trying to serve for like a particular area, or are these the entire grid?
Yeah, I mean, I think I typically think of spinning reserves as more helping on like the bulk energy system as opposed to because I think what you're alluding to is like transmission relief, like congestion relief in certain areas. I mean, it certainly could be possible, but I typically would think of spinning reserves more as not providing congestion relief, just providing kind of supply relief. Yeah.
But that's on like the whole grid.
Yeah.
Alright.
Well, because like you're dealing with these issues with frequency, which propagates through the entire grid. I mean, I suppose it is connected in some ways to transmission congestion, but Yeah, I mean, my general impression is that this stuff is not really designed to like try and provide reliability in that sense. It's just doing this like frequency. It's helping maintain the frequencies. Yeah.
So then with these spinning reserves, are they generating like some power and then they can just easily start generating more if needed, or?
Yeah. So they are essentially on. Yeah.
Is
Yeah.
there another name for spinning reserve that is there to provide peaking support?
Well, so peaking, it actually is closely tied with frequency, because what ends up happening in peak events is your generators are essentially underproducing, right? Because you have a bunch of load that's demanded of the system, and so when you are underproducing, your frequency is essentially dropping. So we're kind of saying the same thing, but if we're now visualizing like peaking in terms of like frequency, essentially what that equates to is like a drop in frequency. So actually, when you peak very quickly, certainly this is like one of the things that would kick in to try and deal with that.
Okay. I guess I interpreted the peaking generator serving an anticipatory role. Like they know what the load is going to be, or probably going to be at 6 p.m., so they are there ready.
Oh, okay. Sorry. So we're talking about we're referring to slightly different things when we're saying peaking.
Okay.
It's related, but you're talking about like peak generators, right?
Yeah.
Whereas I am talking specifically about load that's peaking. And so I guess the distinction is that you're right. So if we anticipate that peak is happening and I can dispatch these peak generators, then I may not need to rely on any reserves to deal with that kind of peak. I guess where you run into trouble is if you haven't forecasted that very accurately and the load peaks suddenly, you may not have the time necessarily to dispatch those peakers.
Gotcha.
And you may count on things like this to respond quickly to give you enough time to get those peakers online.
Okay.
Yeah. And then kind of the even slower non-spinning reserves are things that are not synchronized. They have to come online, sync up with the grid. This takes even longer. And so you're often using the spinning reserves to buy time to turn this stuff on, which might buy you even more time, or it might actually in itself be enough. So supplemental replacement reserves, these are helping restore your reserve margins for the next event that might be happening. Yeah, so the types of resources that we might consider to be non-spinning reserves are like gas turbines that are not currently online, demand response programs, importing electricity from out of your balancing area, and then some slower moving storage. Yeah, so I think the kind of trend, right, is the amount of deviation that each of these services can deal with is kind of like smallest that corresponds to the fastest things, and they're like they're almost these chained together systems that help you buy time so that you're essentially leaning on you're leaning on systems that will eventually be able to deal with that particular sort of contingency event. Okay. So the last thing that I'm gonna mention here, so we've mainly been focusing on frequency, but not all of the reliability problems have to do with frequency. And so things like voltage support and reactive power, yeah, so not everything is about frequency. Reactive power is going to help support your voltage stability and transmission loading capability, and it can affect your generator and motor operation. So if you guys remember, we actually talked about this during the field trip, right? So reactive power, there are mechanisms to help deal with this often at the local level. So like at the substation, that was the bank of capacitors, right, that helped to deal with this particular issue.
Reactive power is like, it's like the initial spike needed when like a motor comes on, for instance.
Well, it's tied to that, but reactive power, oh, we're gonna get into this again. This was that whole analogy about, it's like connected to, essentially the electricity being able to do work, right? And so there's the sort of real power and then the reactive power, which is kind of this like, yeah. It's the bars volt
I wouldn't look at it
analogy.
as a triangle.
Yeah, there's a geometric, well, you were the one who gave the geometric example, right? So it's like,
It's
how did
actually
it,
a circle.
yeah, how does it go again? How are you describing it? I'm trying to remember.
I'm struggling because I subsequently explained it to somebody else.
Oh.
And when I explained it to someone else, I like drew the circle and then used trigonometry, but
Okay.
it's like how did I explain it?
It is, it's a form of power we don't really need to worry about too much in this class. I mean, even at the scales that we usually talk about, the reactive power, the like conditioning of it all happens more sort of locally. And so it is an important aspect of the reliability piece, but it's not often dealt with directly by CAISO. It's more on the sort of wires end. The utility is going to have to deal with it, and there are like specific requirements to make sure that your reactive power is within normal like bounds. Yeah.
Can I just, I guess, take a whack at reactive power and see if I have it understood right?
Sure.
So, I kind of imagine reactive power as being like the time-delayed electrical energy that's currently stored in fluctuating magnetic fields, that's inductors, and also voltage differences, capacitors. Like it's got a bit of like delay to when it becomes real, not active power, I guess, or real power. I did not study
Check out
electrical.
the power triangle. If you Google the power triangle, there's a lot of YouTube videos on it.
Yes. Maybe I'll try and find a good resource that explains it well, because I don't think I can explain it very well. Yeah. But okay, let's press on here.
We actually take a
One more slide, and then we're going to take a break. So the last slide on ancillary services. So these are why these are becoming kind of more important. We have a lot more solar, right? And so this is sort of less physical inertia in the grid because you're no longer spinning like a physical turbine and generator. That actually also corresponds to this idea that we're going to have higher forecast errors simply by virtue of now a greater proportion of our power generation is vulnerable to things like weather, right? And our ability to make forecasts about the impacts of weather is going to increase in variance as you have more of this resource. We've talked about the duck curve, right? This is leading to a lot faster ramping. When you have ramping resources being sort of, I'll say like depleted, right? So we have a bunch of flexible generation, and you use up more of that to deal with this duck curve ramping, then you're like reducing the assets that you have, the flexible assets that you have as a sort of backup. Larger contingency sizes, as you have a lot more sort of build out of transmission. And we'll actually talk a little bit more in detail about this in a moment. And then climate driven stress on your grid. So if you have to like, if you have like PSPS events or other sort of stresses from something like a wildfire, your backup to provide stability in the grid starts to become increasingly important. Okay, so let's take a quick break here. Let's do 4 minutes and then we will press on.
Yeah, no, that totally, that makes sense.
I'll be right back.
Mm-hmm.
For a truck like that can cover its need. But the rules we are working on, there is no other charging stations available for trucks. So if we want to model like charging stations on the road, like what should be the criteria of the modeling? Because we don't want to model it like randomly there should be a charging station. We want to make it kind of complex, but we are not sure about how to do that.
Yeah, okay, so you might have like some kind of route, and then maybe you have specific node locations, right? And the question is, should I here, or here, here.
Also, we want in order to choose like make nice choices, like can we also go to if it's
Yeah.
more like beneficial to leave the road.
Yeah, so this sounds like some kind of like optimization-based question, right? So you're trying to optimize based on the demand, but also cost of the system,
Also,
right?
tariff structures are also in the system.
Yeah. So you can include all of that, and you have some constraints to fulfill, right? You need to make sure that that the fueling station will actually provide the amount of fuel that you need based on the demand for traveling that route. Probably the thing that will make it interesting is layering in the cost piece of it, right? And so, maybe the stations cost different amounts of money in different places. You can set them up in different sizes. Related to this stuff, like you could have different like electrical capacity, and then maybe you need upgrades and that would cost money, right?
Our route is from California and between Utah, like going back and forth.
Yeah.
So horizon, maybe just changing. We actually need to focus on that, but we are still not sure about how to do like direct communications for charging.
Okay. Why don't we talk a little bit more after class? Yeah. Okay, let's press on. So we're going to talk about ramping, net load, and forecast error now, right? So these are all sort of connected to what I was just talking about in terms of the uncertainty that is tied into your system and being able to deal with like contingency events. Okay, so load versus net load. So net load is basically just the load that's demanded, where we subtract away variable generation. Why might an operator like KAISO care about net load relative to load? What do you guys think?
Well, actually, based on their output, right? So you have to be able to meet the load all the time. But going
So KAISO, right, they're responsible for meeting the load at all times, like you're saying. So why are they looking at net load as opposed to just looking at the load to meet? Yeah.
Because when solar are non-dispatchable, you kind of just need to take them whenever you can get them, especially if you're trying to make your investments money back. You just need to immediately use that, but it's not always available. So just like, I don't know, you're trying to follow somebody on the highway, you need to follow that car, not necessarily the flow of traffic.
you may have to curtail as well.
Yeah. Well, so we're going to ignore curtailment for a second, but yes. Yeah, and in fact, right, the answer, I guess, is right there, right? So when we think about what our dispatchable load or our dispatchable generation needs to do, is that needs to meet net load, not load, because the solar and wind is, right, it's non-dispatchable, and you sort of take that up first. Yeah, and so renewable output can increase ramping needs even when total load is flat, right? And so this is essentially the concept of the duck curve, right, that we've been talking about. So, ramping and what it means in practice, right? So not all capacity is the same on a megawatts basis, right? When we think about kind of irrespective of the amount of energy it produces, but how quickly it can produce that energy is actually an important concept and resource. So this is a slide, or these figures provide some context into different aspects of ramping. So on the left here, this is based on the cold start time. So if the generator is like totally off and you wanted to turn it on and produce electricity, relatively speaking, kind of how long would that take, right? And so the fastest ones, hydro and simple cycle gas, right? So these respond very quickly. For hydro, you don't really need to like ramp anything up. You just like let the water flow through your turbine and then it spins, right? For simple gas cycle, you suck air into the turbine, we inject the gas and we combust it and it's up and running, right? Why might the combined cycle and the full ones take a little bit longer?
Boil water.
Yeah, you have to boil water, right? So, you remember that the simple gas turbine of the combined cycle is going to be able to operate almost immediately, but the exhaust heat needs to go through the boiler, and so you may not be like boiling the water from scratch. It might be kind of at a high temperature already, but it takes time for that steam to build up pressure and go through the turbine, and so anything with a boiler takes substantially longer, and nuclear, you have to start up the fission process and boil the water, and so nuclear tends to be kind of the slowest ramping type of asset that we have. This is kind of a nice plot of all of the generators in the US. If you consider how fast they ramp up, this gives kind of the proportions, right? So, you know, about 10% of the generators in the US can ramp to full load within 10 minutes, right? And then another 15% can ramp up to full load within an hour, 30% 12 hours, 30% more than 12 hours.
What happens if you have to have somebody go and open the gate for the water? I'm like, is that factored into this ramp rate, or is it assuming water's already flowing?
Yeah, I mean, yeah, it's not like someone physically needs to go and like lift the gate, right? You just, I suppose there's like a button you press, right? That just like.
Some kind of throttle, but there's a button.
Yeah.
There's
yeah,
a
yeah.
button, but I just mean to say like.
The response time of the guy hitting the button.
Yeah, but KISO, do they actually control dam release?
No,
Like that?
no, no,
That's what
no.
I'm saying. Yeah.
No.
It takes time for them to.
Oh, okay. So, we're talking about maybe slightly different things. So, dam releases can be constrained in certain areas in certain ways. And that is an operational constraint that is, I wanna like physically separate that from the actual mechanism of like sending the water through the turbine. And so the fact that there might be a dam release constraint in a particular area, maybe for like environmental reasons or, you know, for other reasons, that may preclude you from being able to actually run the hydro generator at certain times. But that is not something that would affect the like physical ramp rate of the generator, right? So like absent that constraint, like all of these things, you can just push the button to like turn it on.
Okay.
Yeah.
So it sounds like there's already water coming down.
Oh, okay. I see. I think I
It
understand
takes
what you're
time for
saying.
water to come down.
No. The water is like filled in, and you just have to like let it flow through the turbine essentially. So the idea of like, you don't open a gate and then water comes rushing in. It's filled in everywhere, and what you're doing by pressing the button is essentially opening up the other end so that it can flow.
You're basically opening the shutter. There's a small shutter.
Yeah. Yeah. So, yeah, there's no like water kind of rushing through. Everything's already kind of there, and you're just like letting it go once you press the button. Yeah. Okay, yeah, so duck curve, operational view, right? So midday, high solar, low net load, excess generation risk. In the evening, your solar drops very quickly, your load remains high, and the net load ramps very quickly. And so a challenge for the operator is being able to have enough of that fast moving load or fast moving resource ahead of time, right? And so suppose, for example, that like this stuff is all the lowest cost stuff, and you've decided to dispatch that first, but knowing, despite knowing that you have a really fast ramp coming up ahead. That's a bad sort of operator decision in the sense that yes, you might be economically dispatching in those times, but you're going to run into big trouble once you're not able to deal with those fast ramps. And so that's actually one of the reasons why you might have like slightly non-economic dispatch happening in certain times if you want to value flexible resources to kind of hold back and be able to provide services when you need them. Yeah, and so you want to preserve this upward ramp capability in these evening times. Yeah. Oops, sorry, keep clicking around here, sorry.
Wouldn't a flexible resource bid higher knowing that we would call?
Yeah, so in reality, so there are strategies for some of the ways that they bid, but oftentimes, you know, the operator knows a lot of this ahead of time, and the main thing is on the reserve margins. They keep enough of the flexible stuff paid as a service that you might not necessarily need to be doing, trying to like do valuations of that since it's like baked implicitly into a separate market. Yeah. And then forecast error. So the operator's uncertainty. This is actually a real forecast from KAISO, where you had a particular day that was very spotty with clouds. They do a lot of their forecasts with these auto-regression models, and they tend to perform kind of poorly when you have things like this happening. So very sensitive to weather, behavioral effects, cloud cover, wind ramping, spatial correlation is a common one that you can get wrong when a lot of plants in a particular area get affected by something. Time dependence. If you have day ahead error, there's commitment risk, right, where you've chosen a path that's dispatching or not dispatching sets of generators in a way that will compound your error. And then in smaller timescales, you might run into these issue of running out of reserves if you're leveraging those assets already. And then in the real time, the main error that we've been talking about is with frequency.
What's meant by behavioral effects? Is that just like how people use?
Yeah, suddenly everyone decided to use AC for some reason that you didn't anticipate. Something like that, right? Yeah. locally was like a big one that was coming up with like EVs on like holidays. People would be doing long distance travel and they would get large spikes in demand, right? And so these are these like behavioral things that you didn't see that are happening kind of suddenly.
Like Super Bowl.
Yeah, Super Bowl.
I don't know what you do.
It's like everybody flushes their toilet on
Well, there's that one that the example that I gave earlier in this class about in the UK. Well, this is one that they actually were able to forecast, but like in the UK on Sunday afternoon, there's like a famous program that comes on, and then at the end of the program, everyone puts on their electric tea kettles, and there's I need to dig up that video. It's great. So then you see the operator getting ready, because there's like over a gigawatt of like demand from like electric tea kettles, and the operators are literally watching the TV show alongside everyone, so they know exactly when it ends. Yeah. Yeah. Yes, right. Right, and so forecast error, I mean, I think this is kind of intuitive, right? Why can this be a problem, right? Ramps can be steeper than expected, errors that are correlated, flexible resources are already committed or depleted, right? If you're getting things like wrong perpetually. Yeah, and so you have all these like different failure modes. These are the same things that we've been talking about, throughout. And so managing this is an important aspect of the operator's job. They are not only operating like reserves for supply, but reserves of like ramping resources. They want to, they might be committing flexible units early to deal with certain contingencies, even if it's not economic to do so. Other things that are happening more these days is using storage to absorb excess generation and provide quick ramping capabilities. You might even be curtailing renewables strategically when you have constraints in your flexibility, and then repositioning assets geographically.
Can you elaborate a little bit on ramping reserves?
Yeah. So, when I've talked about reserves in the past, we think about like California, for example. Let's say we anticipate that there's like 30 gigawatts of demand peak on a certain day. That actually means that from a supply perspective, the operator needs to hold back some percentage of generation as reserve, as backup in case like in case the demand is higher than anticipated. We always have backup to work with. That's not the only type of reserve. And that kind of reserve we think of as capacity reserve. This is a ramping backup where you're saying instead of holding back some or requiring some capacity supply, you actually require some ramping supply. So we say you have to keep in reserve X megawatts, X gigawatts of things that can ramp very quickly. And that is anticipation of like load changing fast and not just like having a large amount of load.
And to distinguish that from capacity reserve, capacity is just like sort of a larger bubble that I guess would include ramping reserve, but it's just
Yes.
generally
Yeah.
there for when it peaks.
So reserves often get paid to be a reserve, and so you're kind of sitting back and waiting to get called on, and you actually get paid to act as a reserve, and you get paid as a capacity reserve. You also get paid as a ramping reserve, in a separate financial instrument. Oh, yes.
In the previous graph, what does the percentage mean?
Okay, so this is. All right, let me walk through this. So red dots specify the peak demand in a given day for each month. So that's like the highest load that you'll see in that month. These percentages refers to the amount relative to that peak, right? So for resources, this is the amount of resources that can ramp up within 3 hours as a percentage of the max demand. So if my max demand is 28.3 gigawatts, I have 17.8 gigawatts of capacity that can ramp up within 3 hours. And then I have a lower percentage of assets that can ramp up within 1 hour.
Are those 1 hour assets also included in the 3 hour?
Yeah, so this percentage is actually of the 3 hour assets, what percentage is a 1 hour ramp. So about half of, or a little more than half of the 3 hour ramping can do 1 hour ramping, or in other words, a third of my total max demand. I don't know why they did the percentages that way. I realize that makes it a little confusing, but yeah. So the blue bar percentage is of the red dot, the orange bar percentage is of the fraction of the blue bar. Okay, any other questions? Yeah.
Why is max demand so much higher than this specifically?
What do you think? So this is in California. Yeah, so it turns out like the load demand throughout the year is not always the same because the weather is different. And so what ends up happening here is that you have a particularly hot day where a lot of people are using AC. That's a driver of a lot of these kind of spikes. So you'll typically see in summer months higher peaks. Yeah. Anything else? Yeah, dealing with this stuff is also getting harder. Higher renewable penetration, retirement of more flexible thermal units, the lower system inertia that I was mentioning before, more extreme weather events, a lot of the same type of issues we were talking about for why ancillary services are important. These are the same reasons why forecasts are harder and ramping is more important. All right. So we have talked about different markets before, right? Day ahead and real time. And so now I kind of want to talk about how these things relate to one another, and what is the sort of reality of kind of that planning and scheduling situation, right? So the day-ahead markets produce plans, not outcomes. And then the real-time markets are really about adapting to any mistakes that you've made in the day-ahead market. And so all of this like forecast error stuff and issues that we're talking about, the system operator is built and designed to try and deal with that, right? We know that the day-ahead markets and the schedules are imperfect, and so the real-time markets are the ones that step in to help correct those errors, deal with the uncertainties, and deal with the contingencies. And us having these real-time markets is really, right, the operators literally assuming that the day ahead schedule is going to be wrong. And the question is how wrong and where. Right, so we've talked about the day ahead market and what it's designed to do, right? So we want to predict what load looks like the next day and then commit enough resources to meet those loads. And you're doing this in a very strategic way, right, to ensure that you have enough ramping capability and reserves to meet those loads. You are able to tell what your sort of transmission constraints are going to be, and you're doing this in such a way that you can minimize costs, right? And so the system operator runs these big optimization models to figure out what the schedule should look like in the day-ahead market to do all of this. Once you're in the real-time market, there's a totally different set of priorities, right? So day-ahead market, we want to get things running as efficiently as possible, low cost as possible, make sure all of our reserve requirements and transmission constraints are met. Once you're in the real-time market, you are not thinking about cost minimization. You're thinking about control and security. So schedules are like what's physically feasible, and the optimization, you go from thinking about schedules to what's physically feasible, and you go from optimization to thinking about limiting damage. And so there's a view of different things that you're looking at on the real time that might be a little bit different than what you might be looking at in the day ahead. So frequency reserves, transmission loading, voltages, contingency readiness, all of these things you're kind of keeping an eye out on. Okay, so actions that the operators are taking in the day-ahead market, redispatching generators up and down, right? That's like the tertiary control we were talking about, overriding market outcomes, committing fast start units, curtailing generation, repositioning reserves, and then calling demand response. So these are the same tools that we've kind of been mentioning, and now we're thinking about it in the context of the real-time market. So I want to do kind of a quick walkthrough of this. Yeah, sorry?
Can we go back?
Sure.
You keep reading through these as if we're able to type as fast as you can talk, and that's just not it. I'm not sure what is important enough to listen to and let breeze through, and what's important enough to actually take notes on.
Okay. This stuff is kind of a repeat of a lot of what we've been talking about, so kind of breezing through a little faster here. Okay, so we're gonna walk through a little bit of the sort of operational aspect. So if we are the operator and we're thinking about the sort of generation that needs to happen, maybe on the previous day, I've come up with a day-ahead market schedule. Okay, and so this is just a totally made-up curve, right? But imagine that I anticipate load looking something like this. And so I have this kind of rough scheme of how much generation I'll need. And then, behind the scenes, I'm dispatching, I'm scheduling, I should say, generators to be dispatched in this kind of way. Okay, so let's say our current time is 12:15, so a little bit afternoon. And actually, so I choose this time because I have an outlook 45 minutes ahead. And so there is actually more than one sort of formal real-time market. And the first one that happens is known as the hour ahead scheduling process, or the HASP. This is part of the sort of broader real-time market. So 45 minutes ahead of the hour, they are going to make adjustments to my day ahead schedule, okay? And so in the HASP, basically, I'm over here, and I look at my previous day ahead schedule, and I say, oh, actually, it looks like the load is a little bit higher than I anticipated. Let me adjust my schedule so that I'm actually going to dispatch generators slightly different than what I was saying to do in the day ahead market. So that is we consider this, this type of hour ahead sort of adjustment to my generator dispatch, yeah.
How do operators kind of forecast load for the next day? Like, what do they use to forecast that?
We actually have talked a lot with Kaiso about this. On the day ahead market, there's a lot of data that goes into it, like historical data that helps to feed out what your forecasts look like. But the prime model that builds the forecast is like an auto regression thing. So it looks at previous day, and then it looks at the load from the previous day and a number of input conditions like weather and temperature. It'll also do comparisons against that day in the previous year to see similar trends with seasonality and that sort of thing.
Like a type of algorithm.
Yeah, so there's a complex but yet not actually that complicated sort of algorithm. You feed in some set amount of data, and it's this auto regression model that will spit out a day ahead forecast. The real-time stuff is, similar to in some regards. They are doing some auto regression type of things, but they're feeding it in at a sort of smaller time scale, and there's different types of data streams that are going into it. Sometimes people will go and criticize the data elements that go into the Kaiso forecast, but you do have to remember that this is a ongoing, continuous, live process, and unless you have a data stream that's live, ongoing, continuous, you can't really use it, right, to help with these forecasts. And so they are somewhat constrained, or heavily constrained on sort of the data front. They are very actively looking into improving their short-term forecasts. They're developing new data streams that aren't as really continuous as they would like, but getting information from a bunch of different solar sources that help to improve some of their forecasts on solar generation. And then the big one they're looking into these days is with advanced metering infrastructure, where they're trying to get sampled data from meters, live meters, that will help them with getting more granular pictures of what the demand looks like on the end use. So a lot of stuff goes into the forecasts, but they're getting pushed to improve because of a lot of the electrification and DER stuff is making their forecasts increasingly inaccurate over time. Yeah. Does that help answer?
A lot of stuff.
Yeah.
Is HASP considered a real-time market?
Yeah, I think there's there's 3 components of real time, I think. HASP being kind of the most coarse, and then I'll talk about the other ones in just a second. Okay, so 12:15, 45 minutes ahead, I'm gonna change my sort of hour ahead scheduling and adjust it based on updated conditions. Okay, now we're getting even closer to 1 o'clock. It's 12:45, I'm 15 minutes out, and now I have a real-time unit commitment, and so this is a further correction from the HASP that's happening from this, what we call 15-minute real time. So that's known as RTUC, real-time unit commitment. Right, and as you get closer and closer, essentially you are providing these sort of continuous fixes to any of the like scheduling and commitment processes that you've made. Okay, and now we get even closer to current time. We're now 5 minutes ahead. And now you have something known as RTD, real-time dispatch, and that may provide even a further sort of correction. And so the like idea here is that I've layered in multiple chances to kind of update to real-time conditions. Yeah.
So what's the difference from like a generator's perspective between RTUC and RTD?
Yeah, so why do we have a 15-minute and a 5-minute? There are some things that you can update in 15 minutes that could be more capable to like ramp up in a shorter amount of time. Generally speaking, the less window of time that you have to respond to something, the more expensive it is. So, like, why do we even have the real-time markets, right? If this was correct, this is like the most cost-efficient thing that you could do. You've had to make this green arrow is a correction that you've made in the hour ahead, which is more expensive. And then you had to make another adjustment in the RTUC, which is even more expensive. And then you've had to make this last adjustment, which on the margin is going to be even more expensive. So generally speaking, if you were able to get all this stuff right, you could operate even more economically. And that's why the forecast error is like an important thing to think about with this.
Are these markets that you would like bid into days ahead of time? Like you will guarantee that at like 1 p.m. of
Yeah.
this given day that I will guarantee that I will have like 1 megawatt of
Yep.
very expensive energy.
Yes, yeah. So and I, as a generator, may participate in the real-time market as well. And the cost of the energy that I'm providing there, I'm going to bid in at a higher price because, oh, now I have to ramp, I'm operating less efficiently, it's going to cost you more money to get that energy. So ideally, the operator would want to try and get that unit in and ramped up correctly in the day-ahead market because that'll be cheapest, but they may end up having to pay for the essentially using that flexibility in the real-time market at a higher cost.
Okay. I've been going through the some of the training modules on ISO to try to get a better understanding from just a different perspective.
Yes.
When they explain the day-ahead market, they use the term residual unit commitment.
Okay.
It seems similar to this real-time unit commitment, like you're guaranteeing that like when the time comes, when it's approaching real time, that like you'll be available to ramp very quickly.
Yep. Yeah. So rather than be specific with the term, the basic idea is like you value the flexibility, and that flexibility costs money. And if you use that flexibility, it's going to be more expensive than not having planned ahead.
Generally because you're operating less efficiently, or maybe you have increased staffing costs.
Yeah, so do I actually have a rank order of this stuff? Yes, I'm going to talk about this in
Okay.
just a second. Yeah, so the idea that you can follow the load is operationally achieved through our real-time RTUC and RTDs. And then, your actual generation might look something like this. It's going to be very close to your real-time dispatch, and then the small deviations might be covered by, the frequency stuff that we were talking about with the AGC. And yeah, so the residual imbalances, the very, very small differences between real-time dispatch and RTD are going to get corrected sort of automatically because you're close enough that you're not going to run into the frequency issues. Okay, and so the formal way of describing this concept that we were just talking about, so what is the economic penalty of our forecast errors, right? So real-time markets are more expensive than day-ahead markets. Otherwise, that's why we try and make sure that the forecast errors are small, and that's why we have a day-ahead market instead of just running everything in real time. And where does that cost come from? So you were mentioning that it is the generator operating inefficiently, and that is definitely one source. But actually the biggest one is marginal unit changes between the day-ahead market and the real-time market. So this is this idea that if there is a difference between your day-ahead and real-time, maybe on the day-ahead, had you seen that difference ahead of time, you would have dispatched a particular generator that could have handled that. But maybe in the real time, you can't dispatch that because it's not ramping fast enough, or there are other constraints related to it. So the biggest cost difference is mainly from different generators having to meet the demand between your day-ahead market and your real-time market. Inefficient commitment would be the second one. This is the one that you were mentioning, between having to do startup and minimum run costs, ramping scarcity, reserve depletion, and then there's out of market actions. So having to manually do commitments, things that have to run due to reliability reasons, emergency dispatch. And so the main concept to remember here is that the errors that I'm seeing in the day-ahead market are costly because flexibility is not free, right? It costs money to have, things that ramp quickly on reserve, and this will lead to all of these things that have this sort of economic penalty. Okay?
I guess I'm not really sure why that marginal unit change between day and real time is inherently expensive. It seems like it's expensive because of the next four reasons.
No, this is a separate thing, right? This is a different thing that's happening. This is basically saying it's not even that you have inefficient commitment. It may be that you literally can't commit the thing that you would have wanted to in the day-ahead market simply because physically it can't dispatch in time, for example.
But isn't the burden of the generator because running that generator at that time is expensive?
Yeah, but there's a physical constraint that generator might not be able to respond within that period of time. So let me take a really, really extreme example.
Okay.
Maybe your forecast is so bad that the most efficient thing that you could dispatch would be a nuclear plant. I know this is kind of a ridiculous example, but imagine that your forecast was off by so much. In the day-ahead market, you said, okay, nuclear power plant, actually, I don't need you, turn off. I know I'm treating it as like a regular dispatchable thing, which is, but then now you're like, in the real time, you're like, oh crap, I should have turned that nuclear power plant on. That's actually the most economically efficient thing that could have been operating to provide power. But now in the real time, I can't tell it to turn on because it takes too long. So a different power plant now needs to get dispatched. So that's what I mean by a marginal unit change. It's actually different units getting dispatched in the real time than you would have preferred in the day ahead.
Okay,
Yeah.
thank you.
Yeah.
When it comes to curtailing renewables when reserves are low or poorly located,
Mm-hmm.
is that because like since there aren't many reserves to compensate for that dip that will occur, like they just don't want to use the renewables and like kind of
Yep.
utilize
Yeah, so this is like a weird one to think about. So if you have a bunch of renewables, and then they were operating, and then later on, like the sun goes down, then your ramp becomes even steeper. And so and maybe you just don't have enough ramping resources to deal with that. And so instead, you just like curtail that and then have some other power plant that's running that won't dip when the sun goes down, so that you don't have to deal with that ramping. So yeah, that is a common, well, not common phenomenon. That's a phenomenon that happens when your reserves are low. Okay, so main takeaways here. Day ahead plans the system. Real-time operations is what keeps you alive. And then reliability is important, and operators are going to assume that they're going to diverge from the real-time market, or from the day-ahead market, and thus have to do stuff in the real time to deal with it. Okay, we're at time. I had like one small last section on contingency stuff, but actually we'll cover this very quickly next time. Okay. That's it for today.